In the previous video, I showed you the useful functions map and filter for lifting functions that work on individual elements to functions that work on whole lists. Now when we start to plug these functions together, we can find there's other useful patterns that we can represent using higher order functions. In this video, those two useful patterns I'm going to show you are composition and the identity function. So what is composition? So composition is simply the act of plugging two functions together. So here's an example from the tutorials in week 1. So there was this function called drop spaces, which I've written wrong here. So drop spaces. What does this do? It works its way through a list and drops all the spaces at the start of the list. So just for a reminder, there's drop spaces, hello. And then one of the other tutorial questions was to write a function called drop trailing spaces, which drops the spaces at the end of a list. And one easy way to write this is to reverse the list, drop the spaces at the start, and then reverse the list back again. And this function is an example of a composition of other functions. We've got the input, and then we do a function, and then we do another function, and then we do another function. And this idea of just taking the output of one function, immediately putting it into another function, and immediately putting it into another function is so common that we end up writing a special operator to do this for us, to make it clear that's what's going on. And this operator is usually called compose, and we'll see later on that there's even a shorter name for it. So how does this function work? Well, we can look at the types to start with. So what we're going to do is, if we start over here, we're going to take an input of type A, we're going to feed it into this function, just going to take A's to B's, and then we're going to feed it into this function, which takes B's to C's, and then finally we'll output at the end a C. So let's write this. So we're going to call the B to C function F, we're going to call the A to B function G, and we're going to call the input A of type A X. And then what do? Well, we write this kind of backwards, so we're going to apply F to the result of applying G to X. And this is simply the composition of the two functions. So let's see how that works. So if I write compose drop spaces with reverse, and then write a string that has spaces at the end, then what's going to happen is it's first going to do the reverse, so it reverses it back to space, 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 and then it drops the spaces. And then if I write compose reverse, compose drop spaces reverse, so this has taken this original composition here, and note now it's partially applied, so this itself is a function. And then write this as hello space, 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 then we get the behavior of the drop trailing spaces. Now this doesn't seem like much of a space saving, but the composition operator is so common in Haskell that it's actually given a one-letter name. So it's written like this. So this has exactly the same type as compose above, but now we just write it using one letter like this. And then to write this kind of infix operator, we have to write it in brackets like this. So an infix operator is like plus or times that appears in between its arguments. So now we can write this function as composition of f and g x is f applied to g applied to x. So load that in again. We can write this now as reverse composed with drop spaces composed with reverse is the same thing, or applied to hello is the same thing as the drop trailing spaces. And indeed we can change the definition now of drop trailing spaces. So make a new definition, let's call it drop trailing spaces 1, and we can now write it without even mentioning the argument. So now we can clearly see that what's going on is that we reverse, drop spaces, and then reverse. So these function compositions are read from right to left. We can think of the data flowing in from the right here, being reversed, dropping spaces, and then reversing. And this explains the slightly odd order of the type definition. So you might think composition would have A to B first, then B to C to go left to right, but if you look at the way we actually apply functions like this, that functions always apply to their arguments, then the natural way is for the arguments to be this one happens first, and then this one happens, the first argument happens second. And so it matches the order in which we apply things. So function composition is itself useful for making pipelines. So if you're familiar with Unix pipelines, then you might have seen something similar to this. So let's say there's a comma-separated value file called registered student. And this pipeline, which is actually read left to right in Unix, uses the grep command, or global regular expression command, to look for lines which include CS316, and then it cuts the first field with a delimiter comma. So it's not important really to understand what's going on in Unix here. The point is that we can write similar kind of pipelines where we have one process doing one thing and another process doing another thing, so it's nice kind of modular building, is we can write the same things in Haskell using the composition operator quite neatly and using map and filter. So let's write this function as find CS316 students. And let's say the data is a bit more structured than we had before. So we're assuming that this thing is a comma-separated value file. But let's say we've got a list where there's two fields, effectively. So there's a list of pairs, strings and strings. Let's say the first one is the student IDs, and the second one is the classes they're taking. And so then we're going to just return a list of strings. So a list of string user IDs, registration numbers. So how do we write this? Well, let's think. First, we're going to do this grep. So that's a kind of filter. So with filtering, we've got the registration number and the class. But we can't use the word class, so let's go course. And we're going to look for all the ones where the course is actually equal to CS316. And then, remembering that we're writing these right to left, then we're going to do a map, look for registration number and course, and we just turn the registration number. And then we put this composition operator in between them. So this now quite clearly says what we're going to do is filter, looking for where the course is CS316, and then do a map to just extract the registration number. If you're familiar with relational algebra, you can think these are similar to some kind of projection, filtering and projection, or selection and projection functions. Another way to make this a bit clearer is to put the things in where clauses. So let's have another go at writing this. So we might replace this filter with taking CS316, where taking CS316, now we don't have to use the lambda notation, taking CS316 is the same as just the course is equal to CS316, and get registration number from registration number, and course it just returns a registration number. So now we can read this whole thing as filter taking CS316 and then map to get the registration number. And what would have been otherwise quite a complicated intertwined function, we can now separate into two parts, just filtering and mapping, and compose them using the composition operator. Another example is this kind of pipeline where we do a filter and then we do some kind of aggregation at the end. So next week we'll look at other aggregation functions, usually defined as folds. But for now, we can just sort of find the number of CS316 students by doing number of CS316 students, take the same database, and now we return an int. How does this work? Oops. Number of CS316 students, well, that's going to be length composed with and then the same filter as before. So we can't reuse this filter because this where is local to this function. We've reused the taking CS316, but we can reuse this lambda expression from up here. And now we can test this. Number of CS316 students. Let's say we've got someone with the registration number 1910-01. and they're doing CS313, 1910-01 is also doing CS316, 1910-02 is doing just CS313. So there's one student doing 316, and we can find out who it is. Find CS316 students, it's 1910-01. So if we have composition, we can think of that as sort of a way of adding functions together. And as soon as we think about adding functions together, we could also think about, well, what's 0 mean in this case? And it turns out the 0 in this case is just the function which does nothing. So that is, it takes an argument and then simply returns it. And this is usually called the identity function. And in fact, this is so commonly used in Haskell, it exists in the built-in library, so it's just called ID. And now the point about ID is that it's always safe to replace an ID in a composition of functions with nothing, to get rid of it. So if we cut and paste this, and then let's say we didn't take out the course numbers from the end. We kept the course number, so we're just going to call this version 3. I'm going to change the type. Then we can see this is basically the identity function. So we can replace this whole thing with identity. And then a bit of thought shows that mapping the identity is the same thing as the identity. So this is just going to be ID itself. And then we can find out that just doing the identity in a composition is the same thing as doing nothing. So the identity function may look a bit useless. I mean, why would we ever use a function like this? But it's quite useful sometimes for specializing functions to do nothing. So we might want to specialize the map function to really do nothing in some cases. Or we might find out that if we have two maps in a row, one of which undoes what the other one does, then the composition is identity, and we can use that to simplify another function. So in summary for this video, I've shown you the composition higher order function, which is a useful function that connects two functions together, and it can be used to make pipelines for processing lots of data and taking aggregates. The identity function is the pipeline that does nothing. The identity function is very useful for places where you want to actually say, do nothing.